Good afternoon. I guess I was a little close to my mouth on that one. How's everyone? All set for our second presentation of the day? So we'll do some of the housekeeping duties, as we usually do. So it's our 15th annual, in case people... anybody actually been here for all 15? Oh, one. And I know that guy in the back's been there right there since he's the host of the event. The organizers are the U.S. Green Building Council, East Bay Municipal Utility District. And I'm sorry I forgot to introduce myself. My name's Charles Bolig, and I do work for East Bay Municipal Utility District, San Francisco Public Utilities Commission, the American Institute of Architects Committee on the Environment, and PG&E, which is hosting this event in this wonderful center that we have here. I know Ryan came over the little PA system, said before, for lunches. There's quite a few. One thing is, if you don't mind helping with cleanup afterwards, everything's pretty much compostable in the back of the room. We have locations to be able to put your lunches as well out in the hallway. So make sure when you're done to leave this presentation, you reach underneath your chair and you grab that box and you help me clean up afterwards and put it back in the little bins. We have 41 exhibitors that are here today, so please take a moment to swing by and say hello. They're an important part of the Water Conservation Showcase. They got some wonderful new ideas. Presentation materials, we do not print them, which most of you that have been here multiple times know. They'll be ready online probably the first week in April. They are recorded audio that they're doing, so I've got to be careful what I say on the microphone so I don't get myself in too much trouble. Evaluations, we stopped giving paper presentations, or excuse me, paper evaluations a couple years ago back. You'll get a Survey Monkey in around a week or so about the event. So please take notes on your little handout so you can actually fill out the Survey Monkey. We really, really appreciate what you have to say. We read every single one of them. And we're always trying to make this a really good event. So things that you like, things that you didn't like, things we can improve, ideas that you'd maybe like to see in the future. So when that Survey Monkey comes, if you wouldn't mind taking a few moments to fill it on out, we'd really, really appreciate that. There's CEUs, and let me click to that one real quick. Everybody's joining the social media on this one, right? Okay. Right here. So if you are going to be self-reporting for this class, that's the number. It'll be also on the last slide as well, and you can report that through the USGBC or the IAI or some other CEU accreditation that you wish. Door prizes, at the end of the event at 5:30 in this room. For those of you that are going to got your little passport and you're going to the specific vendors, make sure you drop it in the fishbowl. You have to be present to win the prizes. We got some really good things for you guys to take home. That's right at 5:30 after the last presentation. Fire exits. If in event of emergency in this building, there's back door right here that you'll leave. There's some stairs, that yellow ones, hand railing. We'll take a right-hand turn. We'll go out to the street here. If you're in this area, say if this is blocked, we're going to the front door that you came on in, and everyone's going down the carousel. Everyone know what the carousel is with the Yerba Buena Park? On 4th and Howard. Ryan, did I get that right? 4th and Howard? 4th and Howard. Okay, so if a fire, we leave the building right away. If there's an earthquake, duck, cover, and hold, right? Everyone learned that? Everyone grew up here in California, right? Duck, cover, hold? So, don't leave the building right away. Wait for the shaking to stop because we don't want anything from, like, on the facade to fall down on top of you. There's water dispensers throughout the building, so go ahead and get a little cup and get some water. And once again, those cups are compostable. And lastly, if you have any cell phones, please put them on silent mode. Presentation will be right around 45 minutes with some Q&A afterwards. If you have questions, please save them. However, during the middle of the presentation, if there's a nomenclature that's said or something you just need a little clarification, that's certainly okay to ask, but let's hold the questions to the end. So our presentation, our presenter today is Jeanine Jones from the California Department of Water Resources. She's an interstate resource manager. She has previously been DWR's Drought Preparedness Manager and still works extensively on droughts. She represents DWR and Colorado River Board of California and Western States Water Council, where she is the vice chair. And she's a registered professional engineer for California and Nevada. Please put your hands together to welcome Jeanine.
Thank you. Well, good afternoon, everyone. I hope you're enjoying this dampish weather that we're having, because after this week, this may be about the end of the significantly wet stuff. Although, as you'll hear from my presentation, our skill in forecasting, or the meteorologist's skill in forecasting, is not very good, so we don't know. But anyway, this is the first day of spring. We are transitioning from the winter climate regime to a spring regime, and typically we would expect to be wrapping up our opportunities for significant amounts of wet stuff. So better forecasting, and I'm going to be talking primarily about precipitation forecasting, because that's where the longer lead time occurs as opposed to runoff forecasting. So better precipitation forecasting is something that water agencies, not just in California, but throughout the western U.S. want. Well, what's a characteristic of the western U.S.? We tend to be rather arid. We rely on water that doesn't fall when we want it, where we want it. We have to manage water. We have to move water around, store it for later times. This requires some ability to understand when we might get water, in other words, what's our climate, but also can we forecast our climate. And forecasting is hugely important. Better forecasting would be really, really good. And what I'll be talking about specifically today is that key area that we're really interested in from a water supply as well as a flood control management standpoint, subseasonal to seasonal time frame. And, what's the current skill? Why do we care? And what can be done or are people doing to improve forecasting skill? Now, first of all, a little background on precipitation in the West. Well, we're California. We're different, right? Yeah, we're different. So California has the highest variability at an annual time scale of precipitation anywhere in the United States. Not necessarily the wettest, think Hawaii, for example, but it rains all the time there. In contrast, in California, our climate is characterized by years that swing wildly from extreme dry to very wet, like we had last year, for example. And in fact, Southern California has the record for the United States. So when you have a climate that has inherently a lot of variability in it, it makes your forecasting job much difficult. If you were in the eastern United States, maybe your average annual rainfall at some point is 40 inches a year, and maybe your range is 40 inches plus or minus 5 inches. That's your season. Not a whole lot of variability there. On the other hand, come out to parts of California, maybe your average annual rainfall is 15 inches plus or minus 10 inches. Huge difference in terms of managing water, and this is why we care about it. So, a definition, subseasonal to seasonal, what's that time frame? So, weather models. You turn on the TV news, you get the weather forecaster there, they're talking about their weather models. Weather models are run operationally out to about 2 weeks. So that's one end of the time spectrum. The other end, the extremely long end, would be century-scale climate forecasts, like climate change, for example. And then there's this large gray area in between that's called subseasonal to seasonal. The academic community likes to use the acronym S2S. And that refers to subseasonal, 2 weeks to about 2 months, and seasonal out to about a year, roughly. Some people take that seasonal out to be 2 years, at which point they tend to call it interannual, but it's that kind of time frame that we're talking about. And the Weather Service, which is part of NOAA, the National Oceanic and Atmospheric Administration, produces products that span the whole time frame, going out from today's weather forecast that you check on your phone before you go outside, so you decide if you need an umbrella or not, all the way out to many years. So remember, weather forecast, 2 weeks. That time period we're really interested in from water supply management is beyond that weather forecast to the season. So as a recovering drought manager, and I shouldn't say recovering because I still do plenty of drought, the 2 questions I keep reminding my academic researcher friends from a California perspective I really want to know. It's the middle of November, tell me what the winter's going to be like. Keep in mind, average annual statewide precipitation in California, we get half of it in December, January, February, 75% from November to March. So few key months, very important for us. So middle of November, start of the wet season, I'd really love to know, is this winter going to be wet or dry? And then halfway through the wet season, say around the middle of January, I'd really like to know, will the next 6 weeks or so, the rest of the winter, be wet or dry? Because that's a point that you can use when you're thinking about operating water infrastructure. So the Weather Service develops products across this whole time spectrum, but as I'll get to in a minute, the skill of these products isn't necessarily equal. So if we're interested in drought, and if you're into water supply, you're interested in drought because that's the stressor that you have with respect to water supply, you're looking at events that last for years and can span very large areas, like, for example, an entire state. Difference between that kind of phenomenon and the conventional short-term weather forecast that a meteorologist makes is you're looking at one storm, fairly small footprint, small time duration. Much easier to forecast that than to think about something that goes out in a very long time. The way that weather models work, meteorologists will call them an initial value problem. For all of those who took mathematics or physics way back when, an initial value problem means you get the existing conditions right and then you spin out your model. Well, that would work really well if Mother Nature cooperated, but one of the adjectives that all atmospheric scientists use when they're talking about the atmosphere is chaotic. The atmosphere is chaotic, random, very difficult to forecast. The longer you go out, the more difficult it is. So a weather model inherently is good for a couple of weeks-ish. And at that point, you've lost the skill that was provided by your initial conditions, and you're essentially guessing. So let's look at the other end of the spectrum, way, way out at this century, or even decadal time scale. That's the domain of climate models. Climate models are what's called a boundary condition problem. So you have an initial condition, but really your modeling is focusing on putting boundaries on that condition. And you let your model run, and it can chug out there on your supercomputer literally for a century or two. And you know, if you're going to pick between being really concerned about the accuracy of what you do, you want to be a climate modeler, because they're like surgeons. All their failures die. Climate modeler, you know, you predict what's going to happen a century from now, 2 centuries from now. Who's going to bother you if you're wrong? On the other hand, if you're a meteorologist and you call it wrong, I guarantee you your next door neighbor will be giving you a hard time about how she got absolutely drowned in a storm that he didn't forecast or she didn't forecast. So, you know, different ends of the time spectrum, different expectations with respect to skill. So, the primary source of skill in a conventional weather forecast, and this is taken directly from the National Weather Service's Climate Prediction Center, so this is how they prepare these longer-term subseasonal to seasonal, or S2S outlooks that we'll be talking about. This is actually the list that they use. ENSO, the El Nino Southern Oscillation. Remember ENSO, El Nino? So ENSO is technically means the climate conditions that span from El Nino, neutral, to La Nina. Those are all pieces of ENSO. So that's the thing that they have pinned their hat on for a long time, going back to actually the 1980s and 1990s when they first started generating a lot of research on this. And I should say that that research was in part funded by the big enthusiasm of the science community over the very strong El Nino of 1982-83, one of California's wettest years. You had all kinds of coastal flooding, got all the scientists excited, you know, something to study, oh, this is really cool. And they kind of, you know, got to the thinking that everything could be framed in terms of ENSO. Now, let's say you're in Paris or something, and you're talking to a taxi driver, assuming you can manage some French, and if you were back there in the 1980s and 1990s and you were talking about the weather, they would blame everything on El Nino. Oh, the stock market crashed. Well, that was because of El Nino. Today we blame that on climate change. You would be amazed at the number of things people blame on climate change. Oh, the Packers lost the Super Bowl. Oh, well, that was because of climate change. So there was this definite tendency to look at everything through the lens of ENSO because that was a strongly represented phenomenon in the climate system, and it was something they thought they knew something about. So once you do ENSO, really the next thing is you're starting to talk about trends, which you observe through data, and a number of oscillations. And I'm going to try and avoid acronyms as much as possible, but I do have to mention meteorologists love acronyms. So this is the MJO, the NAO, and the PDO, for example. Those of us who are not meteorologists tend to call them PWAs, phenomena with acronyms, because they have lots of them. But so they look at these long-term or shorter-term patterns or teleconnections in the climate system, and then they start looking at anything else they can get their hands on. Well, remember a couple of years ago when we had that Godzilla El Nino? Very strong El Nino. And, you know, if you listen to the climate bloggers, the TV meteorologists who were getting just a bit carried away there, Southern California was going to need Noah's Ark, and the Pacific Northwest, yeah, they were going to shrivel up and blow away. Hold that thought. So, what the climate community forecast then, and again, these slides are straight out of forecast verification information that NOAA provides. The top graphic is what they forecast. Basically, dry in the Pacific Northwest, wet everywhere else. And this actually would be what they would call a canonical El Nino forecast. Oh, very strong El Nino? Gee, we've had 2 strong El Ninos in the historical record, therefore, this is what we're going to have again. Basic statistics here, you know, 2 events don't, yeah. What we actually got was pretty much the flip side of that. Southern California remained record dry, and the Pacific Northwest had record flooding. So, this was your one of the strongest El Nino events of record. You thought you understood ENSO. Well, guess what? You really didn't. Other things going on here that aren't well understood, well captured in the science yet, well modeled. This should have been a sure thing forecast for the climate community. It wasn't. So this means clearly we need more work in this area. And if you're a water manager, obviously you cannot use this kind of information. So let's talk a little bit more about ENSO, because even today you still hear an awful lot of noise about, well, we're having an El Nino, it's going to be really wet, or we're having a La Nina, we're going to be in a horrible drought, etc. Well, another thing about ENSO, and maybe I'll go back here a minute, notice on the top graphic, which is their canonical version of what happens in an El Nino, where the color shadings are. So the thought process is that in an El Nino, sort of the southern tier of the U.S. gets wetter, northern tier gets drier. Well, you know, nice try, but some parts of the country do respond more strongly to ENSO events than others, and actually the area that probably has the strongest response is along the Gulf Coast area of the United States, the southern, extremely southern part of the United States. But unfortunately, California, we're right there in that gray zone where really there's not a whole lot of a signal except a little bit in Southern California. So this is a scatter plot courtesy of the Western Regional Climate Center at Desert Research Institute showing El Nino, neutral conditions, and La Nina plotted against precipitation. And this is for what NOAA calls a climate division. This is roughly the Sacramento River watershed. This is a part of the state that is most important overall for the state's water supply. So our most water-producing area of the state, and you know, that's a shotgun plot. Take your pick. There's no trend here. There's no skill here. You just get nothing out of this. So forget ENSO for most of the state. Actually, the only place where we see some tendency in the historical record for a relationship with ENSO is for Southern California to usually, but not always, be dry in La Ninas. And if you notice that one blue dot that's called 2011 that's sitting up there all by itself, that was quite a wet year. And that was also a relatively strong La Nina. Oopsie. So, you know, that's what we got with the historical record. You're not going to be able to take this to the bank and use it. And of course, if I were to show you this at a statewide scale, it's just one big shotgun plot. The dots all bunched together, and you don't see anything of predictive value. Well, why do we care about better forecasting? Very important for water management. For example, if you're a reservoir operator, your agency operates infrastructure, it would be really nice to know if we were in a drought, that condition was going to continue or not, so you could make those kinds of decisions about how you operate your reservoir. Let's say that you run a water conservation program, and you're asking yourself, well, gee, so we had a dry year. Well, that was okay. What if next year is dry? I really should probably ramp up my water conservation program, but gee, I have to go to the board of directors, I have to go to my manager, whatever, and ask for more money if we're going to ramp up the program, or ask for new authorities or programs. Things take time to spin up. Or maybe you're on the financial side of a utility and you're saying, oops, if we have a dry year, that means our revenue goes down, and we put off making that rate increase decision for a while now, but we know what happens when revenue goes down. Maybe we should take another look at thinking about doing a rate increase discussion, and we all know that elected officials and your constituents don't like rate increases. So that's not something that you want to just do for fun, so to speak. So lots of decisions we could make. Another example is doing water transfers, either as a drought mitigation or an every year measure. A lot of water agencies like to do short-term water transfers as a dry conditions response tool. Well, we're California. We have lots of laws and regs. You don't just go and do one overnight. It takes time. It takes time to do the environmental compliance, it takes time to go through a permitting process, it takes time to the buyers and sellers to negotiate a contract. A good rule of thumb for a dry year water transfer that needs to be physically moved through the State Water Project or the Federal Central Valley Project, plan in about 5 months. And people, particularly in agriculture, want to make a decision about, are they going to plant, not plant, get water, do what, by March. Some of them would consider that late. April, really late. Well, if you want to be able to do that, you need to know in November which way you're going to which way you're going to lean. Otherwise, you will be finding yourself sitting there in February saying, gee, I got to, I really want to do this, but gee, there's a huge backlog in the permitting process. There may not be capacity to move my water to where I would like it to go, all those kinds of things. So longer lead time, really, really good. And interestingly enough, and I should say as background on how NOAA and the Weather Service have historically worked, because the Weather Service's focus is on this 2-week kind of time frame, when they think about who their clientele or their primary constituents are, they really focus on the emergency management community. Just think about it, 2-week forecast, that's flood, disaster, that kind of thing. And particularly when you look at the country as a whole, it's just in the western U.S. that we have this obsession about water supply, because if you're in the eastern U.S., it rains a lot throughout much of the year, and you're not nearly as focused or as worried about understanding what's happening at different lead times. Well, NOAA and the Weather Service, to their credit, are starting to realize that there's a whole community out there on the water supply side, and folks on the energy side as well, that really want information at these longer lead times. And when NOAA responds to an event, the Weather Service responds to an event, tornado, hurricane, flood, etc., if it's a big event, they do something called a service assessment, which is kind of an internal look-see within the Weather Service that says, well, how did we respond? Did we get the hurricane forecast right? Did we get the track forecast right? Did we get the flooding that resulted from the hurricane right? They did their first ever service assessment for drought on our California drought, published in 2015 for the drought up to 2014, and the major recommendation there was to improve seasonal prediction for water supply. Hello? We've been trying to tell them that for a long time. I'm glad that this is finally getting some recognition, but keep in mind that if you're a federal agency who's headquartered on the East Coast, everyone kind of thinks about things through the lens of where they are. Well, if you're on the East Coast where it rains all the time, you're kind of not really thinking about the situation that we have in the western U.S. And if you're a drought manager, this has been around for a long time. You can look at the after-action reports on all of California's major droughts. For example, 1976-77, this is an excerpt from a DWR publication. And, you know, that is exactly where we are today, essentially unchanged. You know, we can't predict seasonal precipitation. They're trying to predict, the 30-day outlooks have been issued since 1947, but experience shows that success has been modest, with temperature forecasts enjoying more success than precipitation forecasts. Hello? That's exactly where we are today. And then it says, also, it would be desirable to develop additional skill in forecasting the weather month hence. What's needed for water supply management is a long-term projection, at least a year in advance, with a high degree of reliability. Boy, whoever wrote that was optimistic. But still unchanged from today's conditions. And clearly it's in the federal government's best interest to do this, because rough cut estimate of what would it take to make some improvement in this subseasonal to seasonal forecasting skill might be something on the order of $20 million a year for 10 years for the Weather Service. Now compare that to what the federal government through USDA pays out in crop disaster assistance in the western United States whenever there's a big drought. Those are measured in units with a B, billions, not millions. So clearly there's a lot of economic benefit across a variety of sectors, agriculture, energy, water, etc. So, you know, a lot of potential here for improving things. And in fact, in the last, 2010 and 2016, so last 8 years, there have been 2 National Academies studies talking about what do you need from a research perspective to move the skill of forwarding along down the field, so to speak. And the short answer is that it's kind of a little bit of everything. There isn't a silver bullet, so it requires more access to high-performance computing, research, improvements to models, assimilation of data into models, etc. So a little bit of everything across the research spectrum. On the bright side, last year Congress enacted what is called in short form the Weather Research Act of 2017, excuse me. It was actually first brought up in the prior session of Congress, but enacted in 2017, and that has a title in it for subseasonal to seasonal forecasting. Well, that's the good news. The bad news is that, as you know, the congressional schedule has been a bit odd of late. And the bill was enacted based on the language from the prior session, only authorized funding for 2017 and 2018. Oopsie. So yes, we need to get this reauthorized to move forward, but it explicitly tells the Weather Service to do some things, including a report to Congress that's scheduled to come out next month on what it takes to improve S2S forecasting, as well as getting them going on operational week 3 and week 4 temperature and precip forecasts. You know, good start. So we're delighted that some attention is being given to this area, but clearly, that authorization that expired through 2018. So yeah, we need to work on that. So as the NRC reports said, work across all areas of the forecasting spectrum, and it's interesting actually that for those who don't follow science computing, that one of the biggest and most expensive, so to speak, needs that they have is for access to the high-performance computing resources on these big supercomputers, because better weather models means higher resolution models. If you looked at some of the first-generation climate models in the United States, for example, the Rocky Mountains are not there because of the scale at which the climate models operate. So the Rocky Mountains are maybe a little bit of a bump in the landscape. Well, if you're in the western U.S., you all know that precipitation is all about mountain ranges and orographic precipitation. So that means you need to get higher resolution climate models, which means the computing time gets way more expensive. So this is only one of the many issues that's faced in terms of improving forecasting. So, what are we going to do in the interim while the scientists think about this and try to get bigger, faster, better computers and more access to research computing time? Well, something that we at DWR have been focusing on and pursuing is let's kind of, instead of saying let's try to solve the whole problem at once, which is essentially the Weather Service focus is, nationwide scale, going forward incrementally, fix the data assimilation, fix the model again, run the model again. Let's see if we can focus here in California, for example, and let's see if we can take a phenomenological approach and understand the causes of our extreme precipitation and see if that provides a pathway forward. So if we look at, and this is courtesy of our friends at Scripps Institution, if we look at the West as a whole, we see that different phenomena cause extreme precipitation in different parts of the West. No surprise. Now, if you're on the West Coast, it's sort of a good news, bad news situation. The bad news is we have no weather observations in situ in front of us to improve forecasting at the short-term scale because, just not a lot of radar sitting out there in the ocean. On the other hand, clearly, we're very much dominated by this phenomena of atmospheric rivers. And if you were to look at other parts of the West, you would see, for example, in the Southwest, the monsoon, primarily in the summertime, is a big source of precipitation for them, and also important for inflow into the lower Colorado River, which, since California gets part of its supply from the Colorado River, we find that of interest as well. You look at the Great Plains, summer is actually their wetter time, and if any of you have ever seen one of those really interesting, fantastic hailstorms that they have back there in the summertime, you can appreciate what they mean by deep convection. That's meteorologists speak for really nasty storm that you don't want to be outside in. And if you look at parts of the Rocky Mountains, where headwaters area of the Colorado River, then there's a different phenomenon going on there. So, we ask ourselves, can we use this information to help us get some ideas about what we can do in forecasting? So the state of California has invested more than $40 million in the last decade in observing systems for extreme precipitation, meaning atmospheric rivers, and research associated with that. Most of that came from us at DWR, a little bit from the Energy Commission. But we're a little over 10 years into this now, and I'm happy to say that courtesy of this big investment that's been made in the observing system and some of the research that has gone on around it, that we are actually sort of seeing some potential pathways forward. Now, this was all put in with a flood control perspective in mind. Extreme precipitation, flooding, better forecasting for conventional weather forecasting for flooding. But learning about these atmospheric rivers and how important they are to our overall water supply conditions has opened up some new things for us to pursue going forward. So this is kind of a busy slide, so I'll give you a minute to look at this. This is also from our friends at Scripps. The color scheme on those arrows represents essentially strong, weak, medium atmospheric river events, and the arrows are the paths that those storms took in reaching the West Coast. People often call atmospheric rivers the hurricanes of the West Coast. We don't have the winds associated with them, but we have the water. So think of this as being analogous to watching a hurricane track. And what you should see here is that an awful lot of those arrows hit California last year, and in fact our friends at Scripps counted a total of 68 of them for the water year. Remember what last year was like? Very soggy. This is why it was very soggy. Now, hold that image in your mind and let's look at 2015, which was one of our drought years. A lot of atmospheric rivers going up and hitting the Pacific Northwest and British Columbia, very little hitting California. And in a nutshell, California gets most of its precipitation, average statewide precipitation, from a handful of storms. 5 to 7 storms, big storms, are it. That's where the bulk of the money comes from, so to speak. This little drizzly stuff, it may seem, especially like here in San Francisco, that's always drizzly, does not do much for you in terms of big amounts. So small number of storms, big outcome. And why did we not get many storms that year? Because we had what some bloggers call the infamous ridiculously resilient ridge sitting out there. It sent all those storms to our neighbors to the north. So the question then is, can we start forecasting these things like people do with hurricanes? Or can we better understand them? And why is this important from a water supply standpoint when we're talking about lead time on these big events? I'm going to give you a couple of infrastructure examples now. This is a slide courtesy of Sonoma County Water Agency for a pilot project in what's called forecast-informed reservoir operation at Lake Mendocino, so Russian River watershed. And if you have a reservoir, likely, if it's a reservoir of any size, there's a corps of engineers, what we call a rule curve on it, that says that, this reservoir is going to have a flood control function, if you signed up for that when you constructed the reservoir. And that means that you will hold the reservoir down, which is the red or the orange on that screen, the orange-red dotted line. You will hold the reservoir down in the winter to provide space for floods, and then in about April or so, you'll start letting water store in the reservoir, which then you can use in the summertime. Well, let's say that you have a big storm coming in, like an atmospheric river event, and it creates that big spike there in 2012. Well, unfortunately, that big spike happened in the wintertime when you're not supposed to be storing water because you're supposed to keep that reservoir empty for waiting for that big flood. So Sonoma County had to release that water just as we were going into the drought and ending up with very low reservoir levels later on. And, gee, that 100,000 acre-feet of water or whatever it was would have been really useful for them. So, this is an interest that reservoir managers have in understanding these big storms. And my example of, at the beginning, it's the middle of January, it's been dry so far, what about the rest of the winter? Because if I really don't have to worry about a big storm the rest of the winter, I can fill whatever space I have with any little stuff that may come in, and I'll end up better on the water supply side. Conversely, on the flood side, I may be sitting, right around my flood control reservation, but if I could see a series of big events were coming in, like we had last year, I might want to take the opportunity to start releasing water in advance of that, so I'm not worried about how much I'm taxing levees downstream. So this is an interesting concept, and other agencies in California are starting to look at it now, including on the Santa Ana River, where Orange County Water District is just beginning a pilot project on forecast-informed reservoir ops focusing on Prado Dam. There, the interest is in, can we get more water into groundwater storage downstream? Well, groundwater basins don't soak up water right away. It takes time for it to infiltrate, so you don't want to release water too fast. You'd like to hold the water and release it at a rate that the groundwater basin can absorb it. So they're very interested in, if we had better forecasts, could we use it to kind of trickle out that flow if nothing else was coming, so that we could get some groundwater storage out of it. So now the fun part, we'll talk about a couple of research projects that we at DWR are doing on atmospheric rivers. So on the left-hand side of the screen is a graphic from our friends at Scripps that is the probability of experiencing an atmospheric river within the next 2 weeks. So this is on a weather model timescale. This is a weather model that has been specially optimized, if you will, to be good at seeing atmospheric rivers. And what we're seeing is the entire West Coast, and if you could read the tiny little print, you could see that it has latitude on the y-axis and days going out. So starting from 0 time and going out 16 days, actually. And those colorful looking blobs are basically diagrams of probability. So a bright purple blob says very high probability that this moisture that we're seeing out there in the weather model 3 days out and it qualifies as being moist enough to be an atmospheric river, is probably going to hit between these latitudes 3 days out. By the way, I look at this tool all the time during the wintertime because I use it to plan hiking trips, frankly, and anything else I want to do outdoors. This is really good for finding out what the near-term weather is going to be like in terms of really wet. And on the right-hand side, a very experimental project that we have underway with NASA Jet Propulsion Lab. And this entails taking, first of all, we had a model bake-off. So our researchers took the top 13 climate models in the world and rigorously analyzed them with hindcast data to see which of these do the best job of seeing an atmospheric river, identifying it, getting it right. And now they are running them with some experimental research data out of the European Weather Center in a forecast mode, giving us a 3-week forecast. And the graphic I'm showing here, just to give me something to talk from, is an example of what's climatology or average conditions versus what's potential change from average conditions. Now, 3 weeks out, you cannot really forecast this storm going to hit right here. And that's well outside the skill of the science. But what they can say is, gee, you have a significantly elevated probability, say, 70%, whatever the number is, of having an atmospheric river in this time frame within this box of latitude that you're looking at, which is really helpful. So I'm delighted to say that they've been producing these completely experimental, first-time ever forecasts for us this winter. And it's really scary because they've actually been pretty darn correct. This was not supposed to happen when you're doing a research thing with weather models. And because now you're worrying that, oh, they're getting the right answer, but for the wrong reason, which happens all the time with weather models. So it's like, this is really great, but this is also really scary. So we're running this as a 2-year experiment, so I'm going to be really interested to see what happens next year. And here, just for fun, was the forecast from yesterday. So when I said that this little event that we're getting later this week may be it, this is what I was talking about. So all that nice blue color on the larger of the two boxes essentially means no probability. So that one probability cloud, so to speak, is the event that will be hitting, more or less, if I look at the scale from here, it's a little over 2 days, 2.5 days if you're at 35 north latitude. Southern California is going to get the biggest hit out of this. For us if you were to go up to the north coast, say at about 40 degrees latitude, it will be less than a 1-day event there. But, that's what I said about, we're transitioning to a spring climate regime, not much left in the system at this point. So, getting into the wrap-up part now, what might a significant improvement in forecasting entail realistically? Well, obviously it takes money. It takes federal research money because, hello, that's what the National Weather Service and the federal agencies typically do. Mission-driven research on understanding sources of predictability, like we've been doing some experimental work with atmospheric rivers on the West Coast. Models, meteorologists cannot live without models. Grants for research and following up on some of this great data that we've got from the West Coast observations. We're actually also funding a very small research project in the Colorado River headquarters because that's important for the state's water supply as well, just to kind of spin them up to a point where they could be ready to go and ask for federal grants or seek federal grants just to fund some basic climatology there. More computing resources, that's the first thing that the researchers ask for, and pilot projects, somewhat like what we've been doing with our atmospheric rivers in California. So, what can we do as water users or people who would like to use these better forecasts? Well, encourage our congressional officials that do appropriations that, there is some skill here potentially. It's not a lost cause. It just needs focus. This has been a really neglected area in the research community because you've got a very defined weather research community over here, you've got a very defined long-term climate change community over here, and then you have the middle child. So we've been the middle child, and we need to get more focus for the middle child. And of course, NOAA is starting to spin up implementation of the legislation passed last year But as I said, its authorization ends this year. So clearly they need some help to get funding to work on it going forward. And this is where I wrap up and ask their questions.
So I'll come around with the microphone. Does somebody have a question right off the bat? One moment.
Well, there were a lot of places that their reservoirs released the water because of old rules. And it made people really upset because the water just went to the ocean and it was perfectly good water. Is there any way that we could tell them that there's better forecasting and not do that? Can't we have a little bit more time before we release or something? And what about building more storage, too?
So Corps of Engineer reservoir rule curves are essentially constrained either by regulations or by statute. Many of the rule curves that we have were essentially written into the authorizing legislation for the reservoir back when the reservoir was constructed. And changing a rule curve, even through the regulatory process, other than doing what's called a minor deviation in Corps speak, essentially would require a major NEPA process and perhaps statutory authorization on a reservoir-by-reservoir basis. So it's not a trivial process. And you have to, I should say one thing, you have to look at a case-by-case basis. Some reservoirs will get a lot of benefit from this, and some maybe not so much. So you have to look at it case by case. But one thing to keep in mind is that if you think of California's big, important reservoirs, the ones that are particularly large and useful from a water supply standpoint, most of them were designed, just because of when the reservoirs were built, were designed based on the hydrology of the first half of the last century, and were designed before the first weather satellite was ever launched. So in essence, those rule curves take no account whatsoever of the ability to do anything like modern weather forecasting, and a meteorologist would tell you that the skill of conventional weather forecast, just that 2-week time period, has greatly improved over a time span of multiple decades, say since 1950. So there's a lot of opportunity out there, but you have to look at it case by case on the basis of each reservoir, and it's not a trivial exercise by any means.
I actually have a question, and since I do work for a water utility, and I was very kind of nervous about these sort of things because my life can be very easy or very challenging. Now I know that California used the Sierra Nevadas as a frozen reservoir, about 1/3 of our water supply, and I remember a decade or more or so ago that some of the modeling was predicting at that time that the seasonality of our rains will switch from typically November, December, January, shift a little bit later in the year, and that the snow level is going to raise. And then there's an issue with if you get rains in the spring on top of snow, then you get a lot of runoff and a lot of flooding. That was about a decade ago. Has that shifted at all, or is that still kind of it's a funny crystal ball, and it's not really clear, pretty cloudy. So, any thoughts or comments on that one?
I could go on that subject for a long time, but let me pick several different pieces. So, first of all, for example, the long-term climate change models, for example, that our friends at Scripps have been doing for us, suggest that by the end of the century, we will have lost more than half of our present snowpack due to warming. So that's a future projection. But let's think about where we are right now, which I think is the more enlightening thing. So if we look at our two big watersheds, the Sacramento River watershed and the San Joaquin River watershed, more than 90% of the elevation of the Sacramento River basin is below 7,000 feet. That should scare you. The San Joaquin, it's more like 50-50. Now, if you look at, for example, the Colorado River Basin, that's where you really want to be, because most of the watershed there, 15% of the watershed contributes 85% of the runoff, and that 15% is above 10,000 feet. But just look at the warming that has been observed in the last couple of decades, you can go, for example, to the Western Regional Climate Center's climate tracker tool and plot things such as the change in freezing level at Lake Tahoe over time. It's not a pretty picture. It's getting warmer. And if we look at just the last few years, look at the drought, for example. So in 2015, we tied the record for lowest ever statewide snowpack of 25%. We thought that was bad until, did I say, no, that was 2014, until 2015 when we set the record for lowest at 5%. Now, look at last year, 2017, a very wet water year. As a matter of fact, measured in terms of statewide runoff, second wettest on record. The snowpack was nowhere near what it was in 1983, which is the wettest year on record for statewide runoff. And look at this year. You know, statewide snowpack right now around 40% of average. That's not good at all. So if you just look at the data, you can see that, you know, we have a very highly variable climate, but you can see that there's going to be issues with snowpack going forward. So we lose that storage capacity.
Glad I asked a very happy question for everybody in California. Got a hand back here.
This somewhat of a simplified question, but there's a lot of movement for rain barrels and that sort of thing, and I've experimented with that. It seems like that would be a good model for individuals to get a sense of what it is like to manage water storage. Because one of the things I find is they fill up. It doesn't take long for me to use them up, and then there's no rain. So to the point of, you know, why don't we build more storage? It would seem like that's probably the best value of rain barrels, is it teaches you as an individual what it's like to be a reservoir manager. Correct me if I'm wrong, but it seems like a simple model.
Yeah, and you know, one of the other things too is there's something called quasi, which is I won't even bother to try and spell out the acronym, but it's basically it's a academic-based hydrologic network that is now taking over a voluntary program of rain gauges for people to have in their, you know, in their backyard, et cetera, with the idea of getting people to measure and report in. It's a continuation of the old National Weather Service co-op system, which is sadly dying on the vine because it's not getting funded. But the idea of getting people to individually observe what's going on in their area, you know, really has a lot of value to it, whether it's a rain barrel or a rain gauge. You get another question up front here? Right up front here in the end.
Thanks.
And there may have been another one.
Well, then right behind you.
Really quickly, can you speak to how groundwater storage in California might alleviate some of these storage problems?
Well, most people don't realize it, but California already has a lot of groundwater storage now. On average, under average year conditions, about 40% of California's urban and agricultural supplies come from groundwater, and in dry years that percentage can go up closer to 60%. We also have a number of very large groundwater storage projects. It's projects that are specifically designed, operated, and managed to store groundwater, so not an incidental recharge thing. We have about 12 to 15 big ones. Some of the largest ones are more than 1 million acre-feet of developed storage capacity. So to put that into perspective, Folsom Lake is 1 million acre-feet. So we've got a number of Folsom lakes that are already there as managed basins. Certainly there's opportunity to do more with groundwater storage, but like with anything, it costs money. So it's, you know, up to local water agencies or groups of local water agencies to look at projects that may be available in their area and decide if they're worthwhile. Here in the Bay Area, I have to tell you that you're groundwater challenged. You don't have a lot of the big alluvial basins where the big projects are, simply because you've got, the geology is not there. You've got rock, essentially. But if you go into the Central Valley, if you go into the South Coast Plain, that's where a lot of the activity is. And I should say also there's been a lot of state financial assistance to local agencies over the years for those projects.
You can see the influence of being on the left coast, because my question was also related to that. But you also identified this ridge that develops off the coast as the driver, or at least director, of incoming storm fronts. What contributes to the ridge?
We would love to know that. And as a matter of fact, I'm negotiating a scope of work with a contract from my friends at JPL right now to work on that. But, you know, at the really simple scale, if you say, well, why do we have droughts in California? Well, it doesn't rain. Why doesn't it rain? Because there's a high pressure ridge sitting right off the coast sending the storms someplace else. Why do we have the high pressure ridge? That's the hard one. And predicting, is it just going to be a normal ridge that forms and decays quickly, or is it going to park itself there during our key winter months? That's the interesting forecasting question. And so we started out with our pilot projects, if you will, our experimental forecasting, looking at and trying to understand the atmospheric rivers. Well, to use an analogy from gaming, from the craps table, if you want to forecast an atmospheric river, you're basically betting that you can roll a particular number on the dice. But on the other hand, the safer bet on the craps table, and by the way, I don't play this at all, so hopefully I got this right, but the safer bet on the craps table is what they call don't pass. That the person throwing the dice is not going to make the point, because most of the time we don't have atmospheric rivers. Well, okay, so can we predict when our friend the ridge is out there, because that could be really useful from a water supply perspective. And that's a much harder research question, which is why my atmospheric scientist friends are backing out the door when they see me coming. But they're thinking about it, and you know, what things can we do that would add skill to some knowledge about that?
So one more. When's the next drought?
Well, you know, so far we've had a dry winter. We like to say that one dry year is not a drought, however, because drought is really a function of impact at the local level. So if you were to talk to people on the Central Coast today, they would tell you probably that they're just a short step away from their next drought, because reservoir storage there has really not recovered from the last drought. The groundwater levels have not recovered. They haven't been experiencing impacts yet, but if they had another dry year, they might be inclined to start talking about drought. Most of our large urban areas can go 3 or 4 years without significant impacts, because the big urban agencies plan and prepare for water supply reliability. Now, I wish I knew what would happen next year, but unfortunately, do not.
Can we duplicate you?
Okay, Jeannie, thank you very much.